All right, thanks everybody for coming to the special Compass seminar. Today we have my friend and colleague, Damian Rouson. He's the head of computer languages and system software group at the Berkeley Lab. Damian has a PhD from Stanford in mechanical engineering and has held a few faculty positions, City College of New York, University of Cyprus. He's running a non-profit called Sorcery Institute that does education promotion of open source software and scientific tools, I guess, and training. And also a for-profit called Archaeologic Inc., which does software archaeology. And today he'll talk, I almost forgot this. He's also an author of a very popular textbook on software design for scientific programming. I read that book years before I'd actually meet Damian. And I think that's good enough. Today, Damian will tell us about language-based parallel programming for Earth system modeling. Take it away, Damian.
Thanks, Milan. And my book is getting a bit old now. It was published in 2011. I've been meaning to write another one for a long time, but Milan beat me to the punch, so he has a much more recent modern Fortran book, and I was honored to be invited to write the foreword for that one. So, came here this week to collaborate with Milan, and he asked if I'd be willing to give a talk, and so that's what this is. And I'm very comfortable with questions throughout the talk. Some of the material that I want to talk about today is still fairly early in its development, so I'll kind of spend a long time on future work. And so please stop me if you have questions about any of it, because I think otherwise we'll probably have a lot of time left over. We'll see. So I'll have a mostly traditional structure to the talk, where I'll start with an introduction, give you some background and motivation for what we're doing with these different language features, then dive into what the actual language features are that we're using, so that's the methodology portion, some results where I'll talk about performance, so you can see what they buy you, and as I said, the future work. I always feel a bit bored when I write conclusion slides, so I don't have a conclusion slide in here. We'll just get to the end and stop. And in some ways, this kind of loops around a bit, where we may go back and forth between methodology and results some. But the basic motivation is I've been collaborating for about 6 or 7 years now with Ethan Gutman, who was on my first slide. I guess I forgot to mention my collaborators. Tan Nguyen is in the computer science department at Berkeley Lab. My group is part of the computer science department, and he's a staff scientist there. And Jordan Welsman is a student who's working with us. He's on in an exchange program from the UK for 1 year. And Ethan Gutman's at the National Center for Atmospheric Research. So Ethan, for some time, I guess since around 2016, has been focused on this downscaling problem. So those of you who are familiar with atmospheric sciences are probably aware that you have global circulation models that use a very coarse grid, and oftentimes it's hard to get the data that you need out of them for things like regional predictions. And so Ethan has a PhD in hydrology, and he wrote this atmospheric model, the intermediate complexity atmospheric research model, so you'll hear a lot about that today. And you might ask, well, why is a hydrologist writing an atmospheric model? And it's because he wasn't getting the resolution, the data that he needed with the level of detail out of the atmospheric model, so he decided to write his own. And so the basic problem is that if you look at the grid that, at least this slide is from a few years ago, at least at the time, the level of resolution that you'd see in most climate models, you really couldn't represent the topography well. Things like the mountains, which make a big difference in precipitation patterns, the mountains are basically smeared out. You can't really see anything that's there. What he really needed in order to be able to predict what the inputs were for the hydrological models was something more like what you see at the bottom. But if he were to try and run the resolution that he needed for regional predictions with using a climate model, it would take on the order of 10 billion core hours. So that's if you wanted to simulate the continental United States for 150 years, at 4 kilometer resolution and say run 40 scenarios, for example. So that was cost prohibitive. So the model that he came up with was the basic idea behind it was first published in a paper in the Journal of Hydrometeorology in 2016. And Ethan and his collaborators at NCAR figured out that they could use an analytical solution for the flow over topography that would actually get them about 90% of the information they needed at about 1% of the computational cost, if you compared it to running a full physics model. So instead of having to actually solve an advection equation to move the flow through the domain, they can, and to deal with complex topography, they have this analytical solution that handles the certain parts of the advection problem for them. And so what then happens though is that if you look at that reduces the cost of the advection quite a bit. So that ends up only being about 5% of the computation. But you're now left with 90% of the computation being in the cloud microphysics. The good news there is that 90% is independent calculations on each grid cell. So it's what many people would call embarrassingly parallel. So it's quite easy to parallelize. The only thing that maybe is a bit challenging to parallelize is the advection, which requires halo exchanges to deal with nearest neighbor communication across subdomains in the model. So in the initial paper, they did some comparisons over an idealized hill, and they could see that they could get very accurate results with ICAR if they compared to a full physics atmospheric model, that being the WRF model many of you are familiar with, weather research forecasting model. And not just matching an idealized hill, but also looking at actual complex topography like precipitation patterns over the Colorado Rocky Mountains, you can see that with ICAR, the level of detail they're able to obtain gives you a very good fidelity relative to what you would expect if you were actually using WRF. This is just so you can see a pretty picture, some animations of what you can see, what you can get out of ICAR in terms of the level of detail. This has an output time step or output delta T of 1 hour. The actual integration time step that's being used in the simulation is about 30 seconds. And at the time that I met Ethan, I met him because I was teaching a training course on modern Fortran at NCAR back around 2016. And at that time, ICAR was only parallelized using OpenMP, which only works in shared memory, so it had very limited scalability. So you could do runs at a time on, say, 16 cores. But we'll show how we can get up to a lot more cores using the parallel features of Fortran itself. And OpenMP, of course, being an external library and runtime that many people use, but we're going to try and just do all this stuff within Fortran. Question?
So if you had the flow over a mountain and with an analytic solution, I would expect it to be true only for an idealized hill, but
Right.
the pictures you were showing were two-dimensional and complex hills.
Right.
So is the analytical solution available for that complex terrain in 2D?
Yeah, so I think what the analytical solution is doing is it's just dealing with the ground topography. It's so you're able to handle more complex geometries because you're using it. But I think I misstated earlier. There actually is an advection problem being solved. Certainly, at least in the horizontal direction. I think in the vertical direction is where the analytical solution helps you. So, and I'll be glad to share my slides with Milan, but I've got a citation to the paper here that can show you how they were doing it. Okay. So, if you look at the way 90% of parallel codes are written, I've seen actual data from our supercomputer center at Lawrence Berkeley called NERSC, that at least 90% of codes that are running on our supercomputers are using the message passing interface, MPI. That's how they parallelize the code. And as I was sharing with Milan earlier, I had a conversation at the Supercomputer Conference, SC Conference, a few years back with Bill Gropp, who led the development of MPI in the early days. And I repeated to him a common quip where people say MPI is the assembly language of parallel programming, because there's a lot of low-level details you have to use when you're using MPI. You pass data in, you have to tell it what type the data is, what size your arrays are, all kinds of stuff that if the parallel programming model is part of your language, the compiler would know all these things. It would know what type your array is and what size the array is and things like that. What Bill said at the time, he said, when I said it's the assembly language of parallel programming, he said that was the original intention. The goal was never for people to put MPI in application source code. It was that it would be generated by a compiler, much like any other assembly language, right? The problem is that it took too long for parallel programming languages to come along, and scientists couldn't wait. They needed to parallelize their codes. 20 years ago, Fortran went parallel, in the Fortran 2008 standard, which was actually published in 2010, so let's say 13 years ago. So that's how we ended up with that MPI in the application source code. The features in modern Fortran, the latest standard being Fortran 2018, the parallel features are oftentimes referred to as Coarray Fortran. And that term, Coarray Fortran, or CAF, comes from a domain-specific language that was initially an offshoot from Fortran. And it was designed as a syntactically small parallel extension to Fortran 95. One of the reasons I like to mention that is because given that it was originally designed as an extension to Fortran 95, that means that you can take legacy codes and add these parallel features because they were designed to work with Fortran 95. It also means that as Fortran developed, the features were integrated well with other features in the language because the committee could see this coming before the Fortran 2008 standard was published. Coarray Fortran had already been around for a decade, and so when they brought it into the language, it really worked nicely with the other features in the language. The basic idea of Coarray Fortran is that you have an extra set of subscripts that you can add to arrays. So if you look at the simple program that I have there, there's the declaration type foo, and so I've defined a type here that just has one integer inside of it, and you can see two sets of dimensions on that object that I'm calling object. The first dimension is in parentheses, which is what you normally see with Fortran, right? It's been around as long as arrays have been in Fortran. The second dimension, which is just shown as an asterisk here, is in square brackets. What happens is when you add the square brackets, and you can have one or more dimensions there, what you're doing is you're saying, I want a distributed object, and I'm going to launch multiple, what Fortran calls images, in MPI you'd call it ranks. I'm going to launch multiple images, which are basically just multiple copies of my program, and as I change that index inside the square brackets, I'll be accessing data on different images, okay? So Bob Numrick was the original developer of Coarray Fortran. He was at Cray in the 90s, and he said he was thinking about what's the smallest change I can make to the language to take it parallel. So at least from a syntactical standpoint, that's a very small change. You just add square brackets, and now you have a distributed object, okay? And you can call certain functions like this image to tell what image you are, or num images to tell how many images there are total. And there's mechanisms in the language for doing things like synchronization, where if you need all the images to stop at some point, so in MPI this would be a barrier. There's also more loose forms of coordination across images that don't involve barriers, but the sync all statement there is effectively a barrier. And then I'm showing some communication. And one of the things that you can see in that communication is, first of all, we're working here with an object, right? So that means that these features play nicely in the sandbox with the object-oriented programming features that came into Fortran in Fortran 2003. Secondly, you can see that I'm using the colon notation. So I have object 1:2. So those of you who are familiar with Fortran syntax, which is also modeled after MATLAB syntax, if you've seen that. That I'm saying I want to work with two elements here, element 1 to 2, right? And I'm assigning to those. Now notice when I did the declaration of object, I had square brackets there. But if I only want to work with my local data, because remember as I change the index inside the square brackets, I can range across all the images and therefore access remote data. If I only want to work with local data, then I don't have to show the square brackets, which is why I don't have them on the left-hand side in that first, the second if statement there, in that assignment. So, in some sense, this is a minimally invasive approach too. I've actually had the experience of taking a legacy Fortran 77 code and parallelizing it using these features. If I have data that I want to distribute across images, I change my declaration. As you can see, the declaration here has square brackets. If there are times when I don't need to access remote data, then those parts of my program don't change at all. The left-hand side there doesn't even, that might have been the same before I even parallelized this code. Oftentimes, large portions of the code, there's no change that happens at all because they don't need to communicate. On the right-hand side, I'm grabbing two elements from the object array, and I'm saying I want to get whatever's the next image beyond mine, get that data, and that's what I'm going to copy into the elements 1 to 2 of my local data. You can also have three-way interactions. So the last if statement there is saying if I'm image 1, I want to grab data from image 3. You can tell I'm talking about image 3 from the square brackets on the right side. And I want to copy that into data that's on image 2. So there's an interaction between image 1, 2, and 3 in that one statement. So it's nice that it's minimally invasive. You can drop the square brackets when you don't need them. But you also want to be clear when communication is happening, because in distributed memory parallel applications these days, the communication is generally the most important, the most computationally intensive, computationally costly part of the simulation. So it's very important not to hide communication and have it be implicit. So we know when communication is or is not happening based on whether there are square brackets present or not. Right? So that's sort of the basic idea of parallel programming in Fortran 2018, using the features that people refer to as Coarray Fortran. There's also a set of features that are targeting a more fine-grained approach to parallelism.
I gotta go.
Sorry.
Very interesting.
There's also a set of features that are targeting a more fine-grained form of parallelism, usually that you would exploit either with vectorization, vector instructions on a processor, or possibly by offloading to a GPU. And those features are things like do concurrent. And so I wanted to try and find some code to show here that was, so the previous slide was, play code just to demonstrate certain principles. But I wanted to try and find something that was from an actual application, that I worked on, which is why, so this is where I was doing some calculations to check the distance between two curves, one being the known solution and one being the actual solution, the solution that the simulation obtained. And there's a lot of use here of array statements like do concurrent, which is where you're telling the compiler that there are no dependencies between passes through this loop. So it should be able to do all of the loops in all the iterations in any order. And typically in parallel, there are a few exceptions there where you could do some things that would make it, where you would not get the correct result if the compiler decided to parallelize the loop. There's been a lot of raging debate on the Fortran committee. I serve on the Fortran committee about whether to resolve those issues. Most of them are things that I think you wouldn't find in most programs. So let's say in most simple cases, by putting a do concurrent there, you're telling the compiler that it's okay to parallelize that loop. And what's happening with most compilers is that in order to actually get that parallelization, you have to pass a flag when you compile, telling the compiler to do it. So that's sort of your consent saying, yes, I know that I've written this loop in a way that can be parallelized. So it could be, for example, offloaded to a GPU. And there are two compilers now, the NVIDIA compiler and the Intel compiler, that will do that for you automatically. So that if you're writing do concurrent, also array statements and things like that, you no longer have to do things like write OpenMP or OpenACC or CUDA in order for your code to be offloaded to a GPU. And people are getting good results. There's a paper not too long ago by Jeff Hammond at NVIDIA where he was showing that the difference in performance between the automatic parallelization in this, using just the compiler flag versus using OpenACC, maybe 6 or 7% slower in the worst cases, and oftentimes, as fast as the approach that relies on external libraries like OpenACC. So one of the ideas behind this is that there's sort of a philosophy that Dan Nagel shared with me. He was the chair of the North American part of the Worldwide Fortran Committee up until about 5 years ago. And he said what you really want to do is to be able to communicate properties of your code rather than specific optimizations, specific ways you want the compiler to exploit those properties. And so that's what you're doing with do concurrent. You're not actually saying that it has to vectorize or multithread or parallelize. You're just saying there is the opportunity here, right? And then you can let the compiler or runtime decide what the appropriate supporting technology might be. There's one more thing I want to mention that may not as obviously tie directly into the parallel and GPU computing, but there's a set of features that I like to exploit to adopt a more functional programming style in Fortran. The main one is that you can declare to the compiler that a procedure is pure, saying that it has no side effects. Such procedures aren't allowed to modify their arguments, for example. They're not allowed to do I/O. They're not allowed to have barriers, to have synchronization statements or anything that orders segments of your code across images. It turns out that when you adopt this approach, there are several nice results that come out of it, even if you might not think of this as part of your parallel programming feature set. One is, if you call a procedure inside do concurrent, the language standard says it has to be pure. So by writing pure procedures, you're enabling all the stuff that I just talked about, right? Another, if we were to go back to the advection part of ICAR, is that if all of the procedures that you're calling as you're doing the communication for your advection, if they're all pure, then none of them could be modifying, data that the others, would care about. They're just using input to produce output. And there's a way in which I oftentimes take partial differential equations like the Navier-Stokes equations and write them as expressions with user-defined operators. And it turns out that all of the operators that you might have, for example, on the right-hand side of the Navier-Stokes equations, can all execute asynchronously on distributed data if you know that each of the procedures is pure. Related to that is also the ability to declare procedures to be elemental. An elemental procedure is one where you write the procedure as if it's only operating on scalar arguments, but you can actually pass in array arguments. The compiler will then take your procedure and apply it to each element by element, and produce an array result. By default, at least, elemental procedures are implicitly pure. So I make a lot of use of those as well. And one last thing is the associate construct, which is where you can associate a name. You can see, like at line 19 here, where I'm associating a name with a function result. Anytime you associate with an expression, and a function reference is one simple example of an expression, you get immutable state. You get something that can't be changed within that associate block. And that's another important property of functional programming, is working with immutable state. I like to think of things like the keyword chamber there. I like to think of these as runtime constants, in the sense, you have compile time constants like at line 10 and 11, but you can also define something that at least within that block, won't be changed. So I think of it as a runtime constant. Okay. So let's look at where this gets us in terms of performance. And the results I'm going to show you for now are with Coarray ICAR, which was a mini app that Ethan and I wrote to capture the algorithm that needed parallel communication, that being the advection algorithm from ICAR. So then we did a bunch of performance analysis on Coarray ICAR. Subsequent to that, Ethan incorporated the Coarray features into the full ICAR application. So now when you run ICAR, it is a Coarray Fortran code. But these results are from the mini app that we wrote. One of the things that happens when the parallel programming model is built into your language is that it means that the actual parallel programming library that the compiler is using doesn't really matter to you anymore. In many cases, it's MPI. If you're using the Fortran compiler, then you'll also need a library called OpenCoarrays that I lead the development of. And if you use Fortran plus OpenCoarrays, you can write parallel code that runs in distributed memory and out to tens of thousands of cores. But there are competitors to MPI. Most of them have a smaller user community, but one of them is OpenSHMEM. And OpenSHMEM also came out of Cray, like Coarray Fortran. The plot that you're seeing here was where we were comparing some MPI results to some OpenSHMEM results. And we were comparing puts, where as soon as data is ready, you ship it off. The image that produces the data ships it to the neighboring image, versus gets, where the neighboring image grabs the data when it needs it. It tends to be faster to do puts than gets, because basically, as soon as the data is ready, you want to get it moving, right? But the more important thing here is that you'll see that the MPI, so these plots resulted from a conversation that I had at NCAR, where I was talking with Ethan, and the platform that we were running on at the time was an SGI, where even the developer who was writing the MPI library for SGI was at the time telling us, don't use these more advanced MPI one-sided features because they're broken. Most of you who've written MPI or seen MPI in application source code, you've probably seen two-sided MPI where you see sends and receives. The one-sided features, the puts and the gets, can be faster because there's less coordination. There's no two-sided handshake. You can just send data over to another image without that other image being involved. But these are more advanced features of MPI that are harder to program, harder for the MPI implementation to get right. And as you can see, we couldn't get the MPI code to run beyond just shy of about 2,000 images, which means 2,000 cores at the time. So I was talking with Ethan about the problems that we were having, and Alessandro Fanfarillo, who's the first developer of OpenCoarrays, the very first release of OpenCoarrays was basically one chapter of his dissertation. And Alessandro came walking down the hallway because he was working at NCAR at the time, he's now at AMD, and he said, "Oh, have you tried OpenSHMEM?" And I said, "What do you mean?" Because I didn't even know that there was an OpenSHMEM option. But Alessandro's the kind of researcher who always keeps this cool stuff in his back pocket to whip out at just the right moment. And he had written an OpenSHMEM alternative to the MPI runtime library that we had in OpenCoarrays. So without changing a single line of source code, in fact, you could even do this without recompiling your source code. It could be a link time decision. to just link in OpenSHMEM and replace all the MPI. And just with that change, we were able to keep running onto more cores. So that's, for me, I think one of the most important things about using a parallel programming model that's part of your language is that under the hood you could have MPI, you could have OpenSHMEM. My group at Berkeley Labs develops a package called GasNet EX. The EX is for exascale. And at one point we had a GasNet layer in OpenCoarrays. We're now working on GasNet support for Coarray Fortran for the LVM flag compiler. And that one is currently being proposed for adoption by Flang. We're still early enough in the process that it hasn't actually been adopted yet, but the idea is that you could be running Coarray Fortran on top of GasNet, or OpenSHMEM, or MPI, without changing a single line of your source code. And I don't have it in this talk, but I've got some slides that will show you that GasNet outperforms MPI. But you could leave all that decision to the compiler developers or the runtime library developers. Of course, since Coarrays was invented at Cray, they're sort of the gold standard. And for this Coarray ICAR code, when we were using the Cray compiler, we could get all the way out to out to about 100,000 cores and get very nearly ideal speed up all the way out. Right? Another thing that's interesting is that you're writing Coarray Fortran, under the hood is MPI, so in some sense you're wrapping MPI. You would tend to think that if you're wrapping MPI, there's no way you could be faster than MPI. But I have a slightly different take on this, which is that, as I mentioned a moment ago, the vast majority of the scientific codes out there are using two-sided MPI. Because there's less coordination between images involved with one-sided MPI, I think the most accurate, most realistic way to compare Coarray Fortran and MPI is to compare the MPI that people are actually writing, right? So it is true that we're wrapping one-sided MPI, so we can't outperform one-sided MPI, but nobody's writing one-sided MPI. So let's take the two-sided MPI that everybody's really writing and compare that to the one-sided MPI that the compiler can generate for you if you're writing Coarray Fortran. And it turns out that even when Coarray Fortran is wrapping MPI, which is the orange dots, we can get faster results, shorter simulation times, than if you were writing your own MPI. Basically, we're generating better MPI for you. If you're writing your own MPI, you get the X's there, right? So there's a lot, I think, to say for having a parallel programming model as part of the language. I think it makes for a lot more clear code. I talked about all the extra arguments you have to write when you're writing MPI and how hard it is to write your own one-sided MPI. But there are great performance reasons as well. If you compare it to what people are actually doing, you would end up with faster code probably if you're using Coarray Fortran than if you're writing MPI. Okay, so that's all on the advection solver that ended up in ICAR. And you can see that the code scales beautifully. But going back to earlier, I mentioned that the advection is only 5% of the runtime. 90% of the runtime is in the cloud microphysics model. And if you want to start to reduce that, there's not as much that the parallel programming model can do for you. What you really need to be able to do is to either offload some of that work to a GPU maybe, or replace it. So I'll show you how we're trying to replace it with a neural network, which is what brings me to collaborate with Milan, because Milan was really one of the pioneers in developing neural networks in Fortran with his neural Fortran package. So when we started to do some performance analysis on, the actual full application ICAR, one of the things we've noticed is that so we're using this package called TAU, Tuning and Analysis Utilities, and we're looking at timings here for different parts of the code. The full application is at the top. This particular run took about 29.5 seconds. But if you look at where the arrow is pointing, about half of that time is just waiting. Okay? So you wonder, why is that happening? Well, basically it comes down to the fact that there's an order of magnitude difference in how much time each part of the application spends is executing that weight barrier, right? So basically, there's so on the right, on the vertical axis, it says nodes, but just think of that actually as images, or if you're an MPI programmer, think of it as ranks. Okay. So the one that gets its job done fastest only spends 0.7 seconds at that barrier. This might have been a different run because we've got a maximum time there of 35 seconds for the one that spends the most time waiting at that barrier. Okay, so why is that happening? The cloud microphysics model is called the Thomson microphysics model. So you can see at the top there, we're looking at the Thomson module. And a lot of that variability is because of the cloud microphysics. And it's because basically you're simulating a region and it starts to rain in one corner of that region. That's where the cloud microphysics takes the most time, and all the clear regions are just sitting there waiting for that region to finish its job so they can get to the next time step. Right? So this is really responsible for a lot of that variability. Okay. So our idea then is to see if we can replace the cloud microphysics model with a neural network. We're using a deep neural network that's fully connected. Fairly straightforward architecture. I don't know if we mentioned it here. We are using skip connections. We found that tends to make the training converge faster. Right now, you can see that there's, I guess I don't know if we're showing it this way here, but right now what we're doing is we're specializing each neural network to produce one output variable. So we have, in the cloud microphysics model, we have about 10 inputs. We have 8 outputs, so we have 8 networks, since they're specialized to each output, but they all take the same 10 inputs. Now this cloud microphysics model is something that has to happen independently at each grid point. So it's a lot of forward passes, a lot of inference, using this neural network, right? We need to do it. We need to do these forward passes on the neural network 8 times at each grid point, at each time step. So what I'm really interested in then is, when you first think about using a neural network, ideally it should produce results a lot faster than the cloud microphysics. And because it's so much faster, there's probably not enough computation to think about things like offloading to a GPU. But what happens when you have a large batch of inferences that you need to do constantly, every time step? Could we get to a point then when offloading might make sense? So we have some additional strategies that we can use. So I started working on a package that I'm calling Inference-Engine, because initially I thought all I was going to do with it was inference, just do forward passes on these neural networks, and I wanted to be able to do them fast. And you can see there num networks equals 8, as I just mentioned. And I've defined these outputs, this outputs object and an inputs object, and I have a multidimensional set of them, I and j, because we're in ICAR, we're, at least for now, we're doing one column of error all at once. but independently we can operate on different columns, so you can see I and J ranging there. And the basic idea is I want to construct a bunch of inputs, a 2D array of inputs, basically ranging across some horizontal plane. And I'd like to be able to concurrently pass in an entire 2D array of inputs. In Fortran, if I just name the array without showing any subscripts, that means I want to work with the whole array. And I want to get the corresponding 2D array of outputs and do that for each network. And I'd like for that to happen concurrently. The idea here being that I know that the NVIDIA and Intel compilers can automatically offload do concurrent to GPUs, which is my motivation for wanting to be able to use do concurrent. And in order for that to happen, as I said earlier, any procedure you call inside a do concurrent has to be pure. So what's happening on the right-hand side there inside that loop is that for each network, I'm calling a procedure. It has a type-bound procedure named infer. That procedure has to be pure in order to go into this do concurrent block, right? So this is sort of bringing together a lot of what we've talked about so far. So that part is now working. We've validated the inference. As I said, it's designed for large batch inference, and one of the reasons it was developed is that a lot of the alternatives that we looked at, first of all, don't really support Fortran directly. Some might, like the Onyx has a C interface, so you could maybe use the C interoperability features in Fortran to access it. But also most neural network packages, most machine learning packages, are designed to support a much more general architecture than we've been using, at least so far. So far, all of our networks have a uniform number of neurons in each layer. If you wanted to vary the number of neurons in each layer, you would probably end up storing each layer in a separate object, and then you'd have to do procedure invocations, on each of those objects in order to make the passes through your network. One of the ideas that I came up with is that, at least in this simple case, when we have the same number of neurons in each layer, we can use multidimensional contiguous arrays to store everything. And so now we can do one procedure invocation that goes through the whole network. Moreover, that procedure is pure, so we can call it inside do concurrent, which means now we can possibly offload everything as well. We're also using an object-oriented design strategy. Since the Fortran 2003 standard, Fortran supports object-oriented programming. So there's an abstract class or abstract derived type called inference strategy, and then I have subtypes of that extend that type to try different approaches. Right now I've got a couple of approaches implemented, one where I call mapmul because the basic step to go from one layer to the next in a neural network is just a matrix vector multiplication, and one where instead I break that down into a bunch of dot products that are mathematically equivalent. I wanted to try that approach because I wanted to embed the dot products in do concurrent, knowing that these compilers can offload do concurrent. And I'd also like to have some additional approaches that maybe try OpenMP, OpenACC, CUDA, for comparison. So I can I can make a runtime decision which one of these to use. It could even be adaptive based on what kind of system you're on, right? There's a sister package that the student that I mentioned earlier, Jordan Welsman, has developed. How am I doing on time? I guess I should wrap up pretty soon, right? There's a sister package that Jordan Welsman, the student who's working with us, develops called Nextport. And we've been doing our training up to now in PyTorch. So his package takes the PyTorch model, exports it to a JSON file, Inference-Engine reads in that JSON file. So our basic workflow looks something like this. I thought I fixed this slide. We run ICAR, we save some training data. That data gets imported into PyTorch to do the training. Nextport exports that to a JSON file. And then we can import that into Inference-Engine and use it in ICAR to validate. So one of the main problems with this workflow is that each of these bubbles is a different person. We have the atmospheric model. Ethan's the one who really knows that. I mean, I can run it, but he knows the runs he wants to do, so it makes no sense to have him do the runs. Jordan does Tan does the importing into PyTorch and does the training. Jordan developed Nextport, so he can take that model and export it to JSON for us. I developed Inference-Engine. So one of the big problems is that when you have a different person in each bubble, you're looking at the telephone game, right? There's discussion that has to happen each step of the way, and we have found over the course of several iterations, we keep ending up with a model that's not exactly what we need. Sometimes maybe not even the right number of inputs. And so where I'm really going with this, which is the future work that I'm actually here for this week to work with Milan, is that I'd like to be able to do the training at runtime as ICAR is running, which means that I want to be able to do it all in Fortran. And then basically Ethan can train these models, these neural networks, by doing what he already knows how to do in his sleep, which is to run the code that he wrote, ICAR. And that's why I'm here, because Milan already does training in Fortran with his neural Fortran package, and I'd like to add that same capability into Inference-Engine. And hopefully we end up with a better model and greatly reduce the time it takes to train that model, because we don't have all these different steps and all these different packages and all these different people involved.
And once Ethan's training converges, he can just switch to the emulator on the fly.
Yeah, exactly.
Inference,
right.
Without even stopping the program.
Exactly. Yeah. You can run it until your model is trained and converged, and then from there continue with the neural network, no longer even using the Thompson microphysics that was only there to get the training going for you. That's it. Thank you.
Thanks a lot, Damian. Any questions from the room?
Why do you have to keep training? Wouldn't you do the training once and for all, and once it's done, you just infer?
Yeah, yes. But like I said, it's the telephone game. And so what I've been finding is that we keep going through iterations where, so for example, one nice thing about having the neural network in a human readable format like JSON is we can just go in and inspect the weights and biases and see, hey, wait a minute, a bunch of these weights are zero with skipped connections. That basically means that these layers are pass-throughs and all the work is happening at the bottom, which we would never have known, or it would have been harder to notice if it were just a binary data format. So that's why we're doing things the way we're doing them. But the point was, the model wasn't fully converged. At least that's my theory. And so, unfortunately, no one on the team has much experience with training. And I think what happened was, when Tan was running the training in PyTorch, he wasn't giving us a fully converged model. That's just one iteration of how things went wrong. I mentioned how one time we got a model from him that didn't have the right number of inputs, because we're doing a whole column at once. So, we need to do 8 inferences. Let's say you have 15 elevations that you're studying. You need 15 times as many inputs for every neural network. And he handed us a neural network that didn't have the right number of inputs. Basically, I want to just get rid of all the communication and all the back and forth between different packages and just do the training at runtime in ICAR.
So you want to minimize human error?
Yes. Minimize human error.
Finding the optimal neural architecture is an art too.
Yeah.
So that takes a lot of exploration and back and forth.
But that means you have to run the full model to explore. Oh, I see. So you're iterating on the neural net and then running ICAR for inference. So you need multiple training.
Well, ideally
if
you
have
only
like
need
a
one
perfect-
training.
Huh?
If there was no human error, as you said, you really only need one training. The only reason we've had to go multiple iterations on this is human error. But I'm thinking if we do the training at runtime, it minimizes the chances of human error. Like, it's not going to have the wrong number of inputs because the code wouldn't even run if that were the case, right?
Would you have a new network if you change the number of columns in the vertical? That's what I'm doing.
Currently, yes. And, but this is just for testing purposes so that we can actually get this, working. I think eventually we wouldn't want to do a whole column. One of the reasons we're doing it that way now is I think we don't want the network to have to learn things like sedimentation patterns. Actually, maybe it's the opposite. I guess we'd have to have some way to factor that out. Or we'd like to factor that out because it's fully deterministic, or, So I think eventually we wouldn't want to do a whole column at once, but we're just doing it this way for now to simplify things.
Are there any questions from the Zoom audience? No questions. All right. Thanks a lot, Damian.
Coming. Wait.
All right, we have one.
Can you turn your microphone on to ask your question?
Me okay?
Yes.
Yes, hi. Hello. Thank you, Damian, for a great presentation. And thank you, Milan, for giving us the opportunity to listen to Damian give this talk.
Pleasure.
Okay. A quick question was, if you were starting afresh on such climate modeling needs, especially with the kind of the hybrid approach that you have, with the more rigorous model trained with a neural net for parallelization needs, would you start with Fortran now, other than so outside of an installed base of code that you have? If you were starting afresh, would you pick Fortran? Because that's the question that my management wants to know.
Okay, so, well, first of all, you know me well enough to know that the answer to that is yes, but let me say why.
For the audience's sake.
Well, yes, for the audience's sake. Andrei Sertic, who used to be a researcher at Los Alamos National Lab, he's now at a private company that makes DRAM, I think. And he's on the Fortran committee as well. Just a few weeks ago, he posted in, I think, the Fortran discourse about what he's calling fast GPT. He took the GPT-2 model, re-implemented it in Fortran. He said it took him only 300 lines of code, and it's faster than ChatGPT. So I think that if you're going to be working in a high-performance programming language, ultimately, like Fortran, because you're working in climate, then you might as well just stick with Fortran all the way. But I'd also say that even if you weren't going to be, working in Fortran for your ultimate application, just the fact that you can do the training and do the inference faster, with Fortran, that's, really one of the main benefits of Fortran is the speed. So, but not many people have tried it. So I think, there's not a lot known. I mean, have you done any comparisons between Neural Fortran and PyTorch or anything like that?
I had with TensorFlow back in 2019, and again with the refactor a year ago. Competitive.
Yeah.
So I believe it will for deep, fully connected networks. My naive Fortran implementation was about 30%, so not even a factor of 2, slower than TensorFlow. And TensorFlow is very as optimized as it gets.
Yeah, sure.
and very mature. But that tells you that if just a naive implementation can get that close, that with optimizations and with offloading, you can get really far.
Exactly, yeah. So that was without do concurrent, without GPU offloading, right? So all these things that I'm trying to take advantage of, I think there's a pretty good chance we could beat TensorFlow in Fortran, or PyTorch.
There's no reason not.
Yeah.
Why wouldn't?
Thank you.
Sure.
Thank you.
I'd like to inject a little story. I was at a high-performance computing meeting way back in the 80s. Somebody said, well, when are we going to start moving away from Fortran? It's a dead language. And somebody, I wish I remember his name, because he actually won a Nobel Prize in physics, got up and he said, no, it's not going to be a dead language. It's going to be around, though in a few decades you won't recognize it as Fortran, because back then most of us were using Fortran 77 or something. So you all made his prediction right.
I wish I knew the name too, because I've heard that.
Probably Bob Wilson.
So you were saying you were actually there when he said it?
No, I wasn't there. He was at Cornell when I was a graduate.
Okay.
When he left to Ohio State.
Because there's a famous quote that I think you're referring to where someone said, I don't know what the language of the future will look like, but I know it will be called Fortran.
Right. Well, I was at the meeting when somebody basically said that.
Yeah.
And everybody, got into a big discussion. So it's good to see that y'all are doing this still.
So the downside of you deciding to go in Fortran is that you would isolate yourself from a huge community that's doing development in other languages.
Right.
And it's an ecosystem kind of thing.
Right.
You want to live with an environment where people are trading in dollars, and you're the only one holding, I don't know, yens or whatever.
Yeah, and up until fairly recently, I would have been a lot more concerned about that. But the Fortran ecosystem is really growing. Like, there's a lot of, researchers. Are you still under 40?
I'm 38. Yes.
38. And a lot of them under 40, some under 30, who are writing new open source Fortran, like the JSON. I mentioned, reading JSON files. There's a JSON interface that's for Fortran.
But the DOE, for example, just went fully C++ in their suite of software. They have amazing software.
Yeah.
It's just C++ based, and sometimes it talks to Fortran nice, sometimes it doesn't.
Yeah.
And this is optimization library, mesh generation libraries, communication libraries.
Yeah. Well,
dynamic load balancing libraries.
Here's the thing. I mentioned that I'm funded to work on LLVM Flang, which will be Flang's Fortran compiler. It already can compile, most of Fortran 95, a lot of 2003, and quite a bit of 2008. It's not really released in a very easily usable state because they want to get further before they really expose it to the public. But why is someone at a DOE lab funded to work on LLVM Flang, right? And DOE has invested, I don't know the exact number, but I'm pretty sure it's on the order of $10 million, into getting Flang to where it is now. So there's a clear commitment there. The only thing I would say is that I think from the people who are the most influential in the DOE community, the vision is for C++ to be the application language and for Fortran to be a bunch of small kernels that get called on the back end, kind of like we used to write code in assembly to make it faster. Now you'd write code in Fortran just for some specific kernel, right? I would actually like to see Fortran still be the main program, the application. So I have a slightly different vision from most of DOE, but I'd say even throughout DOE, Fortran is not dead. This was 10 years ago, but I left Sandia. I was at Sandia National Labs for 5.5 years. I left there in 2013. And what I noticed when I was there was that if you talk to people in the applied math and CS community, yes, it was all C++. And those are the people who actually stand up and give talks about their code. Other than today, when was the last time you saw a Fortran programmer stand up and give a talk about their code? Okay, so the difference.
About the application.
The difference, though, was that who was actually getting all the science done. I had two people in my department, Jackie Chen who's still there now. She's in the National Academy of Engineering, does combustion research, and Joe Oefelein, he's also a combustion researcher. He left Sandia and is tenured faculty at Georgia Tech now. They wrote two of the most important codes in the DOE community in terms of applications, and those were Fortran codes. But guess what? As far as I can recall, they never stood up and gave a talk about their code. They only talked about the combustion. So there's still a lot of Fortran that's getting the real work done.
So it's a perception thing too. Right?
Yeah. I know that Jackie's code has evolved and some parts of it have been swapped out for C++. I'd be willing to bet Joe's code is still Fortran.
Fortran is the gray eminence.
Yeah. Don't get me wrong. I'm fully sold on Fortran.
Yeah,
It's the language of science. I think it's much more readable than C++. But you see other forces at play.
Yeah.
So
But the ecosystem is growing. There's a lot more open source libraries out there now for Fortran than there was 5 years ago.
Thank you.
Sure.
Thank you, Damian.
Okay.
And thank you all for coming.